I think we could start now. Let me do this. Hey everyone, thanks for coming. We're happy to have Dr. Veronika Dornan today with us. Dr. Dornan got her PhD at the University of Edinburgh, and now she's a postdoctoral fellow research associate at the University of Edinburgh. She's also a member of a Euclid Consortium and the LSST Science Collaboration. And today she wants to talk to us about how we can study the globular cluster systems to constrain galaxy evolution and properties. So please join me in welcoming her.
All right. Thanks, folks. Thank you so much for having me here. I am going to talk a bit about kind of the basis of my PhD thesis, but also about some new stuff that I'm doing at the University of Edinburgh and generally kind of the field of extragalactic globular cluster observations a bit more generally. But first, I was asked to kind of talk a bit about kind of my career path and kind of how I got to where I am. So I'm going to start with that, kind of who exactly I am. As Neil said, I'm a recent-ish PhD graduate from McMaster in Hamilton, Ontario, Canada. I defended my thesis in August of 2025, and currently I'm working as a postdoctoral research associate at the University of Edinburgh with Annette Ferguson's group. Um, I'm also very passionate about astronomy outreach and science communication. You can see here I've got like all decked out ready for a total solar eclipse. We got a portable planetarium, and I've also done some astronomer in residence work at the Killarney Provincial Park here in Ontario. Um, how exactly I got here, though, I'm going to back it up a little bit. I got my undergraduate degree at Mount Allison University, which even people in Canada really do not know what that is. They do not know what it is. They do not where it is. Because it is a very, very small kind of what you would call in the US a liberal arts college. It only has about 2,500 students in total, all undergraduate. And it's in a town on the border of New Brunswick and Nova Scotia that only 6,000 people live in during the school year. That goes down quite significantly in the summer. Um, I was only one of 5 physics students in my graduating year, and in fact, there was only one astronomy faculty member at the university. So it's a very, very small university, but what it kind of lacks in lots of resources for students that bigger universities tend to have, it makes up for in the fact that I got a very, very personalized, very high kind of attention undergraduate experience, which was really useful. The other thing is that Mount Allison, like lots of liberal arts colleges, had a very interdisciplinary view of teaching its students. So not only did I have to take a lot of courses outside of science, but also they developed a lot of courses that were kind of geared to science students to learn about other types. So this was really useful in terms of like thinking about ways that astronomy and physics relate to a lot of other fields and a lot of other kind of areas of the world. These are just a few of the courses that I and my friends took. I took science fiction literature, which was really, really cool. I took women and gender studies in science. I took a kind of life in the universe course that really kind of focused on like the ways that biology and kind of anthropology fit in with the search for kind of life in the universe. And I didn't take this course, but my friends did, and I kind of wanted to take it, which was history of mathematics, which is like learning how to do math the way they did like before zero was invented or base 10, which is also very, very fun. Um, After I finished my undergrad, I went to McMaster University. I did both my master's and my PhD there with Dr. Bill Harris, who's like the globular cluster guy in a lot of in a lot of ways. But also while I was at McMaster, I became very, very involved in outreach and science communication. So this gave me a lot of opportunities to kind of talk about astronomy. So as I said, I was like very involved in our planetarium. We had a total solar eclipse in 2024. Past totality was like right through Hamilton. So I got to like go on the news and like talk about the eclipse. And this past year, I've been writing for Astrobites as well, so summarizing papers for kind of a more general audience. And in particular, like for this, I always encourage grad students. A lot of time you don't have a lot of kind of time, free time to be doing a lot of outreach, but it's not only like kind of a really wonderful way to kind of give back and like kind of spread the gospel of astronomy, but also I found when I started writing my thesis for my PhD that kind of exercising your science communication muscles, even if it is to a more broad community rather than kind of your specific subfield, it does really, really help your science communication, your talks at conferences, how you write your papers. And I always really encourage anyone who has the time and energy to do as much as they can for yourself and your own skills. Um, I'm not sure. So yeah, so now I am a postdoc at the University of Edinburgh. Um, I'm not sure how many of you are kind of like about to start or have just recently gone through kind of applying for postdocs. I found it was a very, very stressful experience. For reference, I applied to like 20 postdoctoral positions. So there's, if you're applying to a lot and kind of not getting a lot of hits, don't worry. That's like very, very common. So don't, panic. But yeah, so I accepted a position working in a Nets group, and this has been really, really helpful because it's allowed me to join a lot of these larger consortiums and collaborations, which has been really helpful in terms of like getting a lot of data to start working with. If any of you want to talk kind of like after this about kind of this path that I've taken or like applying for postdocs or anything like that, please, please, please contact me. I'm happy to discuss it. But I want to talk about globular cluster systems. This is kind of my bread and butter. So a bit of quick background. Globular clusters, basically all galaxies host globular cluster systems. They can be found kind of in the outer stellar halo of a lot of galaxies. In particular, in the Milky Way, we have our kind of disk where we have a lot of stars, but then we also have our outer halo where most of these globular clusters reside. These globular clusters, they're in the Milky Way. I think there's about 170, around 200. We're finding more, but basically all galaxies kind of host some type of globular cluster system. And depending on the size and mass of the host galaxy, the globular cluster systems themselves can range in quite large amounts. So as I said, we have 170 to like 200 in the Milky Way. But once you get kind of to like Andromeda, it's still around a few hundred. When you get down to really, really small galaxies like dwarf ellipticals, it can be like tens or like even less, like a handful. But when you get up to really, really massive galaxies, you can have thousands to tens of thousands as well. So these are really ubiquitous structures within these galaxies. And they're really, really powerful tracers of galaxy evolution, merger history, and tidal disruption that galaxies have gone through. They can host around 10 to the 6 stars. On average, about 5 times 10 to the 5 solar masses. This can vary somewhat. But they're very, very their half-light radii are quite small to enclose all of this mass. So they're very, very dense. And they're extremely old. They're some of the first systems to be formed within galaxies on the order of 10 to 12 gigayears most of the time, which means that they're very difficult to disrupt as galaxies go through these mergers and kind of like pretty violent events. And they're very old, and they hold onto a lot of properties of the environments that they were formed within. So they're wonderful, wonderful tracers when we look at them today to understand how galaxies got the way they did, especially when you have these systems that are so massive. So the big question that underpins my research is, how do host galaxy and environmental properties affect this globular cluster system evolution? What can the globular cluster system observations tell us about galaxy evolution history, which is a bit connected to each other? And most importantly, is this universal across mass scales? Are we going to see the same trends in very massive galaxies, intermediate mass galaxies, and dwarf galaxies, or do they behave differently depending on the size of the galaxy you're looking at? So I'm going to focus a little bit on specifically kind of the role that mergers play for massive galaxies. And essentially, this evolution is really tightly linked the globular cluster system evolution to the host galaxy evolution. And it's tightly linked both in terms of forming globular clusters and disrupting globular clusters as mergers occur. So this means that these mergers, depending on the kind of richness of the merger history of a galaxy, we can kind of see the ways that it can affect the globular cluster system as well. So this is an example from a simulation paper. This is from Newton et al. 2024, where essentially they took 3 kind of test galaxies that all at redshift 0 have the same mass as the Milky Way, but in their histories they had an enhanced, an organic, and a suppressed amount of mergers, and also varied slightly the how early the merger occurred. And what they found was, depending on how the merger history changed, even though all 3 of these galaxies have the same total mass at redshift 0, they have varying richness in globular cluster systems, both in numbers and mass. So here you can see the enhanced galaxy has significantly more globular clusters than the organic or suppressed cases. You can also see this in terms of the disruption and the formation rate of globular clusters. So here again, we have enhanced, organic, and suppressed, the arrows indicating when these mergers occurred. So enhanced meaning there was a much larger major merger, and suppressed meaning a much smaller merger. Here we have the globular cluster formation rate. So as these galaxies merge, it can both dump in accreted globular clusters from the galaxies that were involved in the merger, but it can also create a starburst and form new globular clusters as well. So you can see that there's kind of like these spikes just after the merger events. But at the same time, in the disruption rate as well, these mergers are very violent events. And depending on the mass of your globular cluster and how well the stars can kind of stick together, these events can also disrupt a lot of globular clusters as well. And in fact, the merger events, and if you look at the enhanced line, where you get a lot of globular cluster formation, also create a lot of disruption as well. So you kind of need to look at the ways in which the total mass kind of changes, and in general, kind of the formation kind of beats out the disruption, but it's also something to keep in mind as well. So there's lots of different ways that these mergers can affect the globular cluster system in terms of forming and disrupting. But there's also ways in which we can look at the globular clusters that have been accreted from the smaller galaxies involved in mergers. In particular, it's really, really, we're kind of blessed to have a lot of great data in the Milky Way. So this is from a paper Belakurov and Kravtsov, where they looked at Milky Way globular clusters and tried to see if we could differentiate which were formed in situ within the Milky Way and which were accreted from smaller galaxies that we have merged with. And this is in particular in total energy on the y-axis against z-axis angular momentum. And you can see actually they were able to kind of draw pretty much a line that can roughly tell you whether or not you would expect a globular cluster to be in situ or accreted. So in particular with Gaia, we're able to perform a lot of these detailed what we call chemodynamical studies of Milky Way globular cluster systems, where we're looking at both the metallicities and the kinematics to be able to make inform these kind of classifications. In addition, with lots of Gaia data, we can actually get more granular in terms of where we place these globular clusters on this plot. So this next one is the same plot, same essentially the same scaling, but now we have grouped the globular clusters not just into accreted and in situ, but in fact, which merger events correspond to various groupings of globular clusters. So here, the blue and the orange are in situ bulge and disk globular clusters, and then each other colored grouping corresponds to a different merger event, such as Kraken, Gaia Enceladus, the Helmy stream, Sagittarius, and Sequoia. So These groupings, we can identify them in energy and angular momentum space, but we can also identify them in their age and metallicity relationships. So you can see that depending on which kind of environment these globular clusters were formed in, so all of these were formed in a smaller galaxy that was then accreted into the Milky Way, you can see that their ages and metallicities vary quite differently, all of these plots, from the in situ globular clusters here in the bulge in the disk. You can see that they are much more metal rich and a lot older than all of these other globular clusters. And this has to do with the fact that depending on the environment that a globular cluster has formed within, it will hold on to the properties of that environment even after it has been deposited into a new galaxy. So studying the properties of individual globular clusters in these systems of around host galaxies, you can start to kind of trace back merger events and kind of the history the galaxy has undergone. This is really, really great to be able to do in the Milky Way, where we have Gaia data, where we have the ability to get loads and loads and loads of resolved stars for each of these nearby globular clusters. But I do not look in the Milky Way. I look outside of the Milky Way. My research focuses on extragalactic globular cluster systems. And we have a lot less data about those. So it's a little bit more difficult, but it's still very, very, we can make a lot of interesting conclusions. Outside of the Milky Way, globular clusters actually play a really important role because as we increase distances, we need really reliable tracers of things like dark matter and these galaxy merger histories. So this is a plot from one of the eMosaic simulation papers that simulate these systems of globular clusters. And essentially it's showing how well stars versus globular clusters trace dark matter in these simulated galaxies. And in general, stars trace dark matter extremely, extremely well. It's up here with a Pearson coefficient close to 1. And the green data points, globular clusters, they still do decently well, especially for very, very high mass galaxies. So as we go to very, very high distances where we might not be able to return all of the stars, globular clusters are very, very bright and very compact. So we are able to still use them as excellent tracers of things like dark matter distribution. Once you get color as well, so we're not always able to get good estimates of metallicity for extragalactic globular clusters, but color, depending on how red or blue the globular clusters look, can act as a good proxy for that metallicity. So once you kind of incorporate these colors and look at the distribution of globular clusters, we can also see that this will also help us distinguish and trace out the dark matter profiles as well. This is an example from NGC 4278, where the density profile of the red globular clusters trace out the stellar mass of the galaxy very well, but actually the blue globular clusters trace out the distribution of the dark matter halo very well. In general, for extragalactic globular cluster systems, blue globular clusters tend to have been formed in lower mass, lower metallicity galaxies and have been accreted into the larger galaxies we're observing. And they tend to actually be able to trace out all these accreted globular clusters, be able to trace out kind of the majority of the dark matter that has also been kind of accreted from many, many mergers as well. So having all of this information about distributions of globular clusters and colors, even if you don't have lots of metallicity and kinematic information, can still tell you quite a lot about galaxies' merger histories. You can also use these red and blue globular clusters through just distributions to be able to investigate ways galaxies are interacting with one another. So this is an example of two interacting rather massive galaxies, NGC 3641 and NGC 3640. And all of these data points, the yellow and the kind of triangle ones, are all globular clusters that have been observed around these two galaxies. And when you plot up the difference in distribution between the reds and the blues, you can actually see this kind of like bridge of globular clusters in between these two galaxies, and you can kind of see the globular clusters red and blue that are more associated with one galaxy or the other as they start to merge. And in fact, this paper also found that there were shells around NGC 3640, which is an indication for massive galaxies that have undergone mergers, an indication that a merger has happened. And the blue globular clusters actually traced out those shells as well. So they're also very useful when you have very diffuse structures within galaxies that can be difficult to observe, but these bright compact globular clusters are easy to identify, or easier in comparison. It can trace out those things that you're having trouble seeing. So I also, a big part of my research has been looking at these systems of globular clusters in the context of a scaling relation between the total mass of a globular cluster system against the total mass of the galaxy which hosts it. So this is the globular cluster system halo mass scaling relation. And as you can see, it's very, very linear. It's a linear relationship. So essentially, the higher mass globular cluster system you have, the higher mass you would expect the host galaxy to have as well. This other scaling relations do not have the same linearity. So this is an example of gas mass against total mass for the same range of galaxies. And you can see there's a bit of a knee there as well. Or sorry, this is stellar mass against halo mass. So the mass of all the stars in a galaxy, not just globular clusters. So the question is, in this globular cluster scaling relation, what exactly is driving this linearity? And more importantly, what is driving the scatter in this relationship as well? So how can we use the richness of a globular cluster system for a given galaxy to understand the history that that galaxy has undergone? If you look back at this scaling relationship, in particular, I want to focus on kind of these pink dots up here. These are brightest cluster galaxies, so the most massive elliptical galaxies in our universe. These are galaxies that have experienced very, very rich merger histories and host very, very massive globular cluster systems. So we want to really be able to study these galaxies and understand where they are in the scaling relationship to get an understanding of how those rich merger histories have affected the systems in particular. Unfortunately, one of the issues with this scaling relationship is that lots of different people have different ways of determining the mass of a globular cluster system. And some of the scatter in this relationship might just be due to varying methodologies. When you look at a sample that has all been determined using the same methodology, such as the Virgo Virgo cluster survey, you can see that the amount of data we have available to us really is reduced. And in particular, we don't have very many BCGs because there's really not that many super, super massive galaxies in just the Virgo cluster. So, what I have done in one of my more recent papers was compile a catalog, a small sample of brightest cluster galaxies to fill in this high mass region using a standardized methodology and understand what exactly is going on with the globular cluster systems of these galaxies to determine where they sit on this scaling relation. So if you go over here, you can see that for a Milky Way globular cluster that's only 12 kiloparsecs away, we get lots and lots of information about the star cluster. We can see resolved stars. We can get lots of information about it. We can plot up a CMD for these stars. But when you're looking at BCGs that are 142 megaparsecs away, these are now point-like sources where really all you have to work with are maybe colors and positions. But the good news is we have strength in numbers because of the size of these globular cluster systems. We can do a lot with just that data. So what we did was we had 27 BCGs with HST imagery, and after completeness corrections, we found that these systems have between 10 to the 3 and 10 to the 4 globular clusters within them, which is quite a lot. And we were able to kind of make some inferences about the properties of these globular cluster systems. So we took each image and plotted, identified where all the globular clusters were, and determined also the density of the globular clusters as a function of radius from the center of the galaxy. So here, all of these darker points means there's higher density of globular clusters. We also determined the distribution of red versus blue globular clusters. And as I mentioned earlier, blue globular clusters tend to have been accreted from smaller, more metal-poor galaxies, whereas the red globular clusters tend to have been formed in situ within these BCGs. We can also see actually that these two different subpopulations of globular clusters within these galaxies have differing distributions as well. So here, same thing, darker areas mean higher density. You can see that the blue globular clusters tend to be more extended in spatial distribution, and the red globular clusters actually tend to be more concentrated. Once we have all these densities for these globular clusters, we can plot them up as a function of radius and fit the slope of this radius, so how steep the radial density profile is. We can also plot up the radial density profiles specifically for those red and blue globular clusters as well, and compare the slopes of those. So for this one, the entirety of the system, red and blue together, this is what the slope looks like. And for red and blue, you can see again, we have a steeper red globular cluster profile slope than our blue globular cluster profile slope. Taking all of this data together, we can integrate the total profile, complete for correct for completeness. So identifying from the globular cluster luminosity function where the turnover is and where we kind of are no longer able to recover the majority of the globular clusters and make some inferences about how many must be missing that are very dim in order to get a estimate of the total number. And then multiply it by the average individual globular cluster mass for a galaxy, which for BCGs tends to be pretty standardized. And you get this new scaling relation. So down here are some dwarf galaxies in the local group. All the blue points are those Virgo cluster survey galaxies I showed you earlier. And up here, we filled in 27 brightest cluster galaxies. Zooming in on this, we looked at which properties of the globular cluster system correspond to whether a galaxy sits above or below the average kind of this relationship. And we found that for the globular cluster system radial density profile, kind of how shallow or steep it is, that was the biggest indicator of whether or not a galaxy would sit above or below the relationship. So having a higher or lower mass globular cluster system than you would expect for its total mass. We took basically the amount a galaxy's globular cluster system mass would be offset from what you would expect, the average being this dashed line, as a function of the globular cluster system profile exponent. So we plotted this up here where very shallow systems are over here on the right, and very steep systems are over here on the left. And the amount offset here is up on the y-axis. What we found was that, yes, if you have a very shallow system's steepness, you're more likely to have a more massive globular cluster system for your mass. For a subset of these BCGs, we also had that color information. So we also looked at it as just the profiles of the red versus the blue globular cluster systems. And what we found was, in general, this relationship between profile steepness and amount offset from the relation was really being driven by the red globular clusters rather than the blue, which seems kind of interesting. So what we kind of realized what this was doing was that in general, BCGs, the red GCs tend to be formed within those very massive galaxies, as I said before. And the blue ones tend to be formed in satellites and be accreted. More extended globular cluster systems can be a sign of a major merger. So energy is injected and into the system, and the globular clusters get kicked to larger orbits, thus having a more extended profile. So putting these two things together, what we found was actually VCGs with extended red globular cluster profiles in particular being higher per unit mass on this relationship was more likely the result of major mergers with other massive red globular cluster rich ellipticals. So this was kind of showing that not just mergers being a big driver in terms of the globular cluster system evolution of galaxies, but also the types of mergers are also really important as well. So galaxies that had loads and loads of small mini mergers that put in lots of blue globular clusters didn't actually drive them up very much in terms of having larger globular cluster system masses for the galaxy, but a few really, really major mergers did. So this is one of the ways in which looking at very, very massive galaxies, you can use these globular cluster systems to understand the types of mergers that are really important. Now, in addition, I also took a look at the very, very low mass end of this relationship as well. So as I mentioned before, having standardized data is really important for the massive galaxies, but it's also really important for the low mass galaxies too. So this is kind of that dwarf end regime of this relationship. And in general, data for galaxies with halo masses less than 10 to the 10 solar masses are kind of lacking. And the data that we do have large errors on both globular cluster system mass and halo mass. It's really hard to get accurate counts of numbers of globular clusters in galaxies that have like 10 globular clusters. And in addition, it's hard to determine the total mass of a galaxy when you don't have that many luminous tracers to estimate the total enclosed mass within that galaxy. The other issue is that more than 50% of galaxies with stellar masses less than about 10 to the 7 actually host no globular clusters that we've observed, which also goes kind of against what we kind of know about globular cluster systems. For really, really massive galaxies, they are everywhere. Basically, every galaxy hosts these systems, but not really some really, really low mass galaxies. For some that are way down here, it kind of makes sense, but then you have this big gap between galaxies that host and don't host globular clusters for actually kind of higher mass dwarfs. So that's also something that is kind of a big question: is how universal is this relationship, and what might cause a galaxy to have more or less globular clusters that you would expect for a given mass. So going back to this plot over here, we filled in these high mass galaxies, but now we have this kind of still very sparse region down here for the dwarfs. So what we did in our most recent paper was actually do a complete literature search of every survey, every catalog that has gotten a globular cluster count for a dwarf galaxy, and compiled them together to create this new observational understanding of this relationship. So here, also something that we did was we took values of globular cluster numbers for all of these galaxies and applied a standardized way to estimate globular cluster mass and halo mass as well, in order to make sure that we're comparing everything to one another. So we've been able to really fill in this low mass end of this relationship, and we were able to kind of zoom in a little bit and get a sense of what properties sit above or below, make a galaxy sit above or below this relationship as well. So if we zoom in kind of in on this low mass area over here, we get this view as well. So here we've divided things up in terms of classical dwarfs, so regular dwarf galaxies in that sense. But the purple points here are ultra diffuse galaxies, and the blue ones are what we call extremely low surface brightness galaxies. So here, ultra diffuse galaxies are a class of dwarf galaxies that are, as kind of the label suggests, very, very diffuse. So they have surface brightnesses less than or greater than 24 magnitudes per arc second squared. And they're also pretty big. They have effective radii more than 1.5 kiloparsecs. We also identified these galaxies that had that same low surface brightness criteria, but they were a bit smaller than the criteria needed to be a ultra diffuse galaxy. So in general, these are very kind of still quite diffuse galaxies, still very low surface brightness. And they can have a range of globular cluster richnesses, but in general, we found that systematically, they tend to have more rich globular cluster systems. And basically all of our extremely globular cluster rich galaxies in this dwarf catalog were all very diffuse, low surface brightness galaxies. So this kind of indicated that there can still be quite a lot of scatter in this relationship, even when you control for kind of methodological mass conversion methods. But even when you control for that, you still have this population where we're seeing that being kind of low surface brightness or diffuse tends to mean that you're more likely to have a much richer globular cluster system for your mass than you would expect for classical dwarfs. We also see this same result actually pop up in a recent Euclid paper where they looked at just the dwarf galaxies in the Perseus cluster. So these galaxies actually were not included in our catalog, and we still see the same trend where when comparing low surface brightness to high surface brightness dwarfs and diffuse to compact dwarfs, you also see this systematically increased richness in amount of globular clusters. It's even more present when not just looking at low surface brightness and diffuse, but specifically looking at ultra diffuse galaxies that meet both of those criteria at the same time. You also see this really big difference in amount of globular clusters that they host. So this is kind of really interesting, and it's one of the ways in which we think that globular clusters can be a really key way to distinguish formation pathways of ultra diffuse galaxies, because we still don't really understand how they form or why they are this way. There are many theories of ultra diffuse galaxy formation. One of which is that they could be considered failed galaxies, so galaxies that occupy actually quite massive halos, so potentially Milky Way mass dark matter halos, but formed most of their stars in a really early burst. So they formed a lot of globular clusters, but then didn't go on to form as many stars. So in actuality, they might have not be sitting on that same stellar to dark matter halo relationship that most galaxies sit on. Their mass to light ratios might be different. Alternatively, they could also be what's called puffed up dwarfs. So they may have had energy injected into them via multiple close passages with other massive halos. And this could expand their stellar distribution and stall star formation through this tidal heating. So it would essentially have the same effect, where you have lots of globular clusters, but we've stalled the stellar formation, and that's what's kind of causing this weird lots of globular clusters but not a lot of stars situation. In general, what this means is from this paper where they kind of got some good estimates of total halo mass based on some good kinematics of the globular cluster systems of a few of these UGGs. They found that this could potentially mean that these UGGs do actually sit where you would expect them to on the globular cluster halo mass relationship, but they don't. We're kind of we're underestimating their halo masses when we kind of try to determine it based on mass to light ratios. There's lots of other kind of theories for how these galaxies form, and we still really don't have a good idea. if you want to learn more, this review that has just recently come out is a really, really good primer on the subject. And I really recommend you take a look at it. In particular, there's still a lot of kind of debate, and in particular, there's this idea that ultra diffuse galaxies, there can be lots of different formation pathways. And it's also, I'll note, not a good sign when a lot of the papers in a field end with a question mark in the title. That probably means that there's still a lot of work to do. But also, not all ultra diffuse galaxies have very, very rich globular cluster systems. If you go back to this plot over here, you can see there are a few that have more poor globular cluster systems than we would expect for their mass. And in addition, this is seen for others as well. So this is probably an indication that there are lots of different pathways, and some might create very rich globular cluster systems, and others might create much more poor globular cluster systems as well. So studying these GCs around these galaxies is really important. So I'm going to kind of wrap this up in terms of kind of what's next in this field and the ways in which kind of these next generation telescopes that have recently been launched in the past 5 years or so has really been helping this field of extragalactic globular cluster system studies. In particular, in general, we're very limited to low redshift galaxies to study extragalactic globular cluster systems. So we don't have a good idea of how a scaling relation like the globular cluster system halo mass relation changes with time, because we're limited to the galaxies in which we can actually recover the globular clusters. So this is from a simulation paper where they simulated the evolution of a bunch of different galaxies, and they kind of made some predictions for how this relationship might change as a function of redshift. But the good news is JWST is helping us start to look at very least the most bright globular clusters, the brightest globular clusters in higher and higher redshift systems. So we're starting to get kind of a glimpse of what this relationship might have looked like at earlier times. So this is an example of globular clusters that we can identify through some ideal lensing opportunities with JWST. So all of these here are potential globular clusters at redshift like 10, which is really, really crazy. And some of these systems also were previously imaged with the Hubble Space Telescope. This is an example of Sparkler, the Sparkler galaxy with HST. This is a redshift of like 1.4. With JWST, we can actually get much higher resolution and pick out these individual globular clusters around this lensed galaxy. So this is really, really exciting, the kind of difference in resolution that JWST can give us in order to pick out those globular clusters. The telescope that I am kind of most excited about, because it's the one I've started working with, is Euclid, actually. So Euclid is not going as deep as JWST, but it has a very, very large field of view and a comparable resolution to Hubble. So one of the things with identifying globular clusters is because they are quite compact and small, as you increase your distance, you need really good resolution in order to pick them out. This blue box is the Hubble field of view. The red box is a Euclid field of view. So you can see the ways in which we're really kind of expanding just how many globular clusters we can identify. This is a view of the Fornax cluster, and all of these little kind of like cutouts here, those are all the areas that Hubble has imaged. But with Euclid, we can actually look in between these galaxies, and we can start to identify globular clusters, all these red data points that sit in between galaxies in groups and systems. So this will really allow us to kind of expand out and find globular clusters in the outskirts of the halos of these galaxies, or globular clusters that sit in between galaxies in dense systems. This is an example from an early data release paper from Euclid where they looked at NGC 2403, and they're actually able to identify 35 new globular cluster candidates around this galaxy. So just by kind of looking at farther out areas than was previously imaged with Hubble. So all of these small squares are Hubble and JWST pointings, but now we can look at the whole thing. In particular, this is important because for a galaxy like NGC 2403, when you look at where it sits on this relationship, it's kind of on the lower end of the scatter of this relationship. But once you add in those new 35 globular clusters, it gets bumped up actually to the higher end of the scatter. So even just identifying a handful of kind of outskirt globular clusters with the large fields of view of Euclid can really change our understanding of the scatter in this relationship. So it's really important that we kind of get as complete a view as we can for these globular cluster systems, especially for the low mass galaxies where just a few will make a big difference. My current project that I'm working on is really utilizing this large field of view of Euclid. So we're using the data release data of data release 1 data to search for GCs in the MAU1 group. And this search is covering 38 square degrees of sky. So this is kind of a circle around MA1 with a 3.5 degree radius. I've kind of highlighted some of the major galaxies in this group, but there's actually a lot more that are even dimmer kind of out here as well. And we're really aiming to complete a very comprehensive survey of the globular clusters in this group, going out much further than previous surveys have, and looking at the ways in which globular clusters can trace out tidal features of this still very interacting group of galaxies. So this is really exciting stuff, and it's really exciting the ways that Euclid is going to help us identify lots of globular clusters that are just sitting outside of the footprints of previous surveys. So I'm going to wrap this up, but in general, kind of the key takeaways that I want everyone to kind of think about is that globular cluster systems, they are very, very useful in studying galaxy evolution. And the more data you get, like color, metallicity, physical distribution, kinematics, they can help you distinguish between globular clusters, where they were formed, whether it was in situ or accreted. And globular cluster populations can help us not only determine the kind of merger histories of massive galaxies, but also understand formation mechanisms of dwarfs like ultra-diffuse galaxies. And telescopes like Euclid are really going to help us expand our understanding of these systems as well. I've left up my email if anyone wants to kind of email me after this if we don't have time to get to your question, but I would love to kind of open this up for discussion with everyone.
Thank you, Veronika. Is there any question for Veronika? Yes, I can.
Hello. It's a great talk, by the way. I feel like I learned quite a bit. I have kind of an annoying question. It was about the completeness correction that you applied.
Yeah.
I don't really know much about completeness correction stuff. So I guess can you explain a little bit more? And I think what I gathered is that you assume a luminosity function and then kind of like fill in the rest. Is that like correct?
Yeah, so this, I kind of breezed over this to kind of get to the results, but yeah, I'm happy to get more into this. This methodology really only works well in terms of looking at it in terms of BCGs, where our understanding of what that luminosity function should look like is very well established. And we're working with a tremendous amount of globular clusters, such that we can make these corrections a bit more broadly. A completeness correction like this would not work with a much smaller galaxy where you only have a handful. But essentially, yes, we kind of take all the globular clusters that we identified in the image. What we did for this work was actually we injected artificial star clusters in for a varying amount of magnitudes, and we saw how we determined like how many at what magnitude were able to be recovered by our photometry software. So essentially, with those artificial stars, or star clusters in this case, you know what magnitude you can no longer reliably return them. And about like 50% completeness is what we take as saying anything dimmer than that, we can't really reliably say that we're getting correctly. And then you go into what you are fairly confident the globular cluster luminosity function looks like. You take that magnitude that you no longer can reliably return things, and then yeah, you do a completeness correction and say, well, if the rest of it we think it follows this luminosity function, then about this many are missing that we're not observing. Yeah.
Okay, awesome. Thank you very much.
Hi. So I have a quick question. When you look into the relationship between the mass of the globular cluster and the mass of the halo, you're referring to the typical mass or average mass of a globular cluster in a galaxy, right?
Okay,
yeah, okay.
So this plot here.
Yeah.
So these I should have maybe been more specific about this. So these plots, this relationship is the mass of all of the globular clusters in the galaxy added together. So here for a galaxy of, let's say 10 to 14 solar masses is the total mass of the galaxy, and the vast majority of that is going to be the dark matter halo. We would expect for this relationship for it to have about 10 to the 9, 10 to the 10 solar masses in its globular cluster system. Over here, when we're doing our completeness corrections, once we have a number, we multiply it by the average mass of an individual globular cluster in a galaxy. There is also a relationship between the average mass of one globular cluster and the mass of its host galaxy. This has to do with the fact that the bigger a galaxy is, the more likely that the globular clusters will also be more massive. But in particular, when we're looking at this relationship, this is the mass of all the globular clusters together.
So it's mostly the number of clusters rather than the mass of each individual cluster, right?
Yeah, so there are two ways that when you look at this relationship, sometimes it will come up in papers, especially for lower mass galaxies. So over here, this is still system mass, this is still system mass. I don't actually think I put a plot up, but a lot of the time for really low mass galaxies, they will actually plot it as number instead of total mass. So sometimes you do see it as a number instead of a mass. But also plotting it up as mass is also important as well, because as I said, for a different galaxy, a different globular cluster system, the average mass of that globular cluster can also vary, and the kind of mass distribution function can also change as well. So especially for kind of like, if I go back over here, kind of like intermediate mass galaxies, this kind of matters a lot because you can actually get good estimates for each individual globular cluster of what their mass is. And you can see some really interesting kind of trends there as well that's also related to the merger history.
Okay, thank you.
Okay, is there any other question for Veronika? Thank you so much, Veronika. Thanks. Let's thank everyone.
All right, thanks for having me, guys.
Thank you.